I'm going to continue classical introduction, classical results. This is not a research program by any means, but just to introduce you to established results in the theory of stability, instability, and so on. And so we were talking about stability, Lyapunov's theorem, Lagrange-Dirichlet theorem, Chataev's theorem for instability, and we would like to adapt, to continue, we'd like to adapt the Chataev instability theorem to mechanics, and let's say in particular to conservative finite dimensional problems in mechanics. So, so let's suppose we have some ball enclosing the origin. The origin is our equilibrium, and an expansion of the potential energy, the conservative case, in terms of the variations, the kth variation, k plus 1, and so on, so that, let's see, yeah. So these are all the variations, and this is effectively a Taylor expansion of the energy. And we know that these variations are homogeneous. The kth variation is a homogeneous function of degree k, so we can write this where u is the normalized q divided by its norm. So we can factor out the norm q to the k power and then have this expansion left. So the leading order approximation then to the energy divided by the norm of q to the k is given by the kth variation evaluated on this unit sphere on the set of unit vectors, like so. So let's consider two possibilities. We know if we have a positive definite energy, then we have the conditions of the Lyapunov theorem satisfied. We have stability. Let's consider two cases. First, a special case where the kth order variation is negative definite. That is, it's strictly negative for all non-zero q. Then we'll consider the less restrictive case, which is more common in mechanics, in which we simply have an indefinite kth variation. So let's look at the simplest case first, where we have a negative definite kth variation. So that, in particular on the unit sphere then, the kth variation is strictly negative. And so from this estimate, the potential energy itself can be made negative for sufficiently small q. So the energy has a local maximum then at the equilibrium, q equals 0. So let's make a vector consisting of the positions and momenta, and we're going to try to construct a Chataev function so that we can prove, we can fulfill the conditions of Chataev's theorem, which is a set of sufficient conditions for instability. We'd like to know in what sense are these complementary to the Lagrange-Dirichlet minimum energy principle for stability. So let's look at a candidate function, u of x, a potential, let's say a candidate Chataev function, which is the inner product of the momenta with the configurations, the q's. So in 2 dimensions, this would be a function with a region. We need a region in which u is positive, and that region should include the origin, which is our equilibrium point. Okay, so clearly this is a function which has that property, and the set of configurations, positions and momenta, where this u is 0, includes the equilibrium. So this has the beginnings of the ingredients for a possible Chataev function. Okay. And so we want to look at a trajectory coming from some initial condition, and we'll use the normal form of the equations, or in terms of the Hamiltonian, the canonical form of the equations. Here we have a purely conservative problem, so there are none of these additional so-called non-conservative forces in this particular instance. The Hamiltonian, remember, is just the total mechanical energy, and the initial condition involves then an initial configuration and momentum. We need to show that the derivative of this function u is positive in this region U+, where U itself is positive. If we can show that, then we have the conditions of the Chataev theorem satisfied, and we can prove then instability of the equilibrium. So we evaluate this derivative on the trajectories of the system, and let's see, we will need the kinetic energy written in terms of the momenta. Remember, because the mass matrix is positive definite, we can interchange the velocities and the momenta freely and rewrite the kinetic energy in terms of momenta in this way. And the G is just essentially the inverse of the positive definite mass matrix. And so we have the Hamiltonian written in terms of Q and P. And the terms we need in the expression for U dot include P dH dP, which is just this. The kinetic energy is homogeneous to degree 2 in the momenta, so Euler's theorem tells us this, that these derivatives are just twice the kinetic energy. And we also need the H dQ so that we can compute this combination in the expression for U dot. And we have this. It's just a calculation. And we substitute in the expression for U dot, and we have this expression here. Here this H is just this, this is essentially the inverse of the mass matrix, and then its derivatives with respect to position. And these are, under our assumptions, continuous functions of the Q's. And this quadratic form can then be bounded below by the minimum eigenvalue of H times the squared norm of P. In our case, we're in the case when these eigenvalues depend continuously on the Q's. And at 0, at Q equals 0, we have simply the inverse mass matrix, which is positive definite. And so this, at 0, this reduces down to the kinetic energy at Q equals 0, but non-zero momenta. That's strictly positive for all non-zero momenta. So at Q equals 0, this minimum eigenvalue is strictly positive. And because it's continuous, then it remains strictly positive for sufficiently small q. Okay? So the leading term in this expression for U dot is strictly positive for q small enough, in a small enough neighborhood of the origin, the equilibrium. We need to look at the energy as well. This is the other term in the expression for U dot. That's this in terms of the variations. Replace E by its variations, kth order, k plus 1 order, and so on. Remember, these are homogeneous of degree k, so Euler's theorem tells us that these combinations, for example, q dE dQ is just k times E sub k, and so on. And so U dot reduces to this. And under our hypothesis, which was that the energy is negative definite at the origin, we can make this, we can ensure that this is strictly negative for sufficiently small q. And so with the sign here, we have something that's strictly positive for q small enough. So if we look at this region, and this is not a good picture, QP space, and q is small enough, we can guarantee that U dot is positive in a region that is contained within U plus, so that the configuration, the origin, which is the equilibrium, is then unstable. Okay, so this simply is a kind of a sketch of a proof that a maximum in the energy will produce instability, and the route to that proof is via Chataev's theorem. The usual case in mechanics, however, is different. We usually have a situation in which the kth variation is merely indefinite, which means for non-zero q, we can assume both positive and negative values. And this is always the case when k is odd, as we mentioned before. In this case, we can also prove that the equilibrium is unstable. Okay. Okay, so let's proceed as before and introduce our state consisting of configuration and momentum. This time we'll show that this U with h the Hamiltonian, this is our previous h, but we're modifying it by the multiplication of minus the Hamiltonian. This will turn out to be a Chateau function in our case. So in this indefinite case, the kth variation, there's a q star at which it's strictly negative. Some q star, not 0. We can normalize it and assert then that there's a u star on the unit sphere where the kth variation is strictly negative. And just by construction of this kth variation, this continuous function, right? So there's a portion of the unit sphere where containing u star where ek is strictly negative. So graphically that's more understandable. So for example, in 2 dimensions, here's a u star where, let's put this here, a u star where the kth variation is strictly negative. By continuity, then there's a neighborhood of u star on the unit sphere where this is also true. And we can construct then a cone through the origin, multiply by norm q, and q then, this q lives in a cone containing this portion of the unit sphere. Okay. And in this cone, then by the homogeneity of the kth order variation, we can assert that for any q in this cone, the kth variation is strictly negative. And remember the energy, expanding it in terms of variations, and using the homogeneity of that energy, we have this. So that for q in this cone, we can guarantee then that the energy can be made for sufficiently small norm q, sufficiently close to the origin, the potential energy is then strictly negative. Remember the Hamiltonian is involved in this candidate Chateau function. At 0 momentum, that just reduces to the potential energy. So when q is in this cone, the Hamiltonian will be strictly negative at 0 values of the momenta. Okay? If we're sufficiently close to the origin. This is a continuous function of p. So if p is small enough, then for such q we can make the Hamiltonian negative by virtue of this inequality. So we can assert then that the Hamiltonian is strictly negative when the momentum is small and provided that q is in this cone with q sufficiently small. So let's pick such a q, small enough, to make the Hamiltonian negative at 0 momentum, and then pick p such that this inner product is positive, so we're in one-dimensional problem. So x, the state is in R2 then. Then we have these sectors PQ positive. Pick such a p with p small enough to make the Hamiltonian strictly negative. We've already seen that we can do that. So then we can construct, in other words, p small enough so that in these darkened sectors here, we guarantee that these conditions are met. So such a state yields then a positive function u, and therefore a set u plus where u is positive, which is what we need in the construction of the Chateau theorem. And the set u star where u is 0 includes the origin. It's defined either by 0 Hamiltonian or the inner product pq is 0. This is at the origin, whereas this is includes the origin. Okay. So this is another essential ingredient in our proof. Now we evaluate u dot on any trajectory of the system, invoking the fact that the Hamiltonian is conserved on any such trajectory. And we have this from before, and this as well. So for small enough q and for such p, in other words, for q in C and p of sufficiently small norm, we guarantee that u dot is positive. And so we can force the trajectory to escape a sufficiently small ball surrounding the origin. And that proves instability in the case of an indefinite energy. That's always the case if you have, if the kth variation, if k is odd. So if you have, for example, if you have equilibrium, so the first variation is 0, and you have the second variation being 0, which we called before the critical case, when the stiffness matrix ceases to be positive definite. And if you have a non-zero third variation, then you guarantee instability. That's the indefinite case, for example. So some simple illustrations of these things, trivial sort of problems. A spherical pendulum, for example. You have a mass under gravity, a massless rigid rod, and we use spherical coordinates to parameterize as the generalized coordinates, say theta and phi. We can write the kinetic energy in this way. The power of the gravitational force, it can be written in this way, and then by comparison of this with phi dot, we find that there's one generalized force, we call it q phi, which is just so. And we can establish just by integration the existence of a function E whose derivative is the generalized force, and that gives us our so-called potential energy. And if we plot that, we find this, obviously. And so at the minimum, we have, when phi is 0, the pendulum hangs straight down, we have stability by virtue of Lyapunov's theorem. And at the maximum, we have instability by virtue of the Chitaev theorem. This is the negative definite case at an equilibrium point. Some more interesting examples just to illustrate the theorems so far. We'd like to establish a connection between, just illustrate the connection between these energy theorems, minimum or indefinite energy, implying stability or instability. Illustrate them through simple examples where we can actually study the dynamics completely. Here's a classic problem, so-called snap-through instability. So we have a single degree of freedom problem in which the mass can move vertically, and some massless springs, unstretched length L, and so on. And we're going to apply a force that we control. So we prescribe the force of a certain fixed intensity. That we can easily show is a conservative problem now. And we can construct the total energy, which is the energy, potential energy of the forces acting on the mass, the spring potential energy, there are two springs, and so on, so it's easy to do. Here x is, x will be position measured from the unforced configuration where the springs are relaxed, let's say. So x is the 1 degree of freedom. And the applied force has a power like so. The force is fixed, we assign it, and so there's an energy associated with that as well. And the total potential energy of the system is just this, where here is our applied force, which we prescribe. And the kinetic energy then, and the Lagrangian we can construct easily. And we can write down explicitly Lagrange's equation. There's one equation, of course. And we find this equation of motion, which is a very unpleasant nonlinear equation, of course. But we know a lot about this system because it's a conservative problem. No damping here. And so we generate a first integral, the conserved Hamiltonian. Kinetic plus potential will be a constant in time. It's convenient to rewrite the equations as a system, and I'll use x1, define such that it's 0 when the mass is on the same line horizontally with the levels of the springs, and x2 is just the velocity of x1. And write the kinetic energy then as a function of x2, the potential energy is a function of x1, etc. And this will normalize our Hamiltonian in this way to make it dimensionless. So this gives us an integral of the motion. V is just the rescaled potential energy. And the thing of interest here is a parameter alpha, which is the unstretched spring length divided by the horizontal projection of that length. So that's always greater than 1. And the trajectories in phase space, x1, x2 space, are given by this. And so we can plot those easily. Okay. The equilibria, of course, are just given by the first variation of the energy being 0, which is just a derivative in this case. And that derivative is this. And we also need the second variation, which is this. And we notice that that second variation is strictly positive whenever x1 it satisfies this inequality, strictly negative in this case, and equal to 0 in this case. Okay? So this means the potential energy has 2 inflection points in general. And if we want the so-called critical load, that's the equilibrium state at which the second variation vanishes, is incipiently equal to 0, then we impose equilibrium at the upper inflection point, the positive root of this equation. That's the value of x1 above the horizontal. Okay, and that inflection point is here. So we're interested then in a sequence of prescribed forces increasing from 0, and you have a sequence of equilibria associated with them that satisfy the first variation equals 0. And then we're interested in the first state that is encountered when the second variation vanishes. And that's called the critical load. Okay, so here's the case of no load. x1 has this value. And at the critical load, we compute x1 here, which is such as to make the second variation vanish. And F sub c is the value of the applied force that must be produced to achieve this configuration. Okay? And the critical load has this particular value, which is not of interest to us. So then we can correlate the behavior of the potential energy with the behavior in phase space, the dynamics of the system. Fix a value of the force between 0 and the critical load, let's say. Then our potential energy, if we plot that energy, looks like this. There are 3 equilibria, 3 places where the variation of the potential energy is 0. And in the phase space, that corresponds, of course, to x2, which is the velocity equal to 0. So there are 3 such points. And here, by the Lyapunov theorems, these are stable equilibria, so initial data in a neighborhood of these equilibria will remain in the same neighborhood of these equilibria. Here we have the negative definite case, and the equilibrium, the corresponding equilibrium, is unstable, as we know. But if we knew nothing about Lyapunov or Chateyev, we would be able to draw these conclusions just from inspection of the phase trajectories of the dynamics. So this is simply an example for students to convince them that the theorems that we've been looking at are actually meaningful. We can increase the force a little bit above this value f0. What we'll find is that these equilibria come closer together in terms of the configuration x1, but the qualitative behavior is exactly the same. At the critical load, that's this case, this is the indefinite case, where for some x1 the energy decreases, and for others it increases. That's the indefinite case. And we prove that we have instability in that case. The phase trajectories confirm that, of course. So there are 2 equilibria. These two have coalesced and coincide now with the inflection points have also coalesced, and we have this. So, and then this is at the critical load. Above the critical load, if we plot the energy, it looks like this. Now there's only 1 equilibrium. The energy is a strict minimum there. And the phase trajectories look like this, and we see that that equilibrium is stable from a purely dynamic analysis. There's another way that engineers might prefer to understand this behavior, remember that equilibria satisfy first variation of the energy equals 0, and that's this. So if we solve this for the force, or demand that this should be 0, we've obtained a function of x1, the configuration, which is simply this. So this is the equilibrium value of the force required to maintain configuration x1. Okay. And if we plot that in comparison with the associated phase trajectories, we have this. So we assign the force, say it at this particular value, then we have 3 equilibria. This is the equilibrium force configuration relationship. So if we assign the force, in this case we'll have 3 equilibria, as we know from the phase diagram. We can represent the energetics in terms of the equilibrium value of the force. So for any x, for any x1, any configuration, the first variation is like this. We can recast it in terms of the equilibrium value of the force. That is, here we prescribe the force. This is the force required to maintain equilibrium at the configuration x1. So obviously when f equals that value, we have no first variation and we have equilibrium. But we can use this to generate a convenient expression for the second variation in terms of the equilibrium force configuration behavior. So then we can say if we have a configuration that's equilibrated, so that the f is equal to the equilibrium value for that configuration, then the second variation would be positive if the slope of that response is negative, unstable if it's positive, and then we have the critical case. So if we go back to the previous slide, these branches where f prime is negative are stable. This branch is unstable, and then at the critical load, that corresponds to F equal the critical force, we have a situation which we have to examine a little bit more carefully. We can assert, in fact, that the configuration is unstable at the critical load. That's the place where the slope is equal to 0. The second variation is also equal to 0, so the second variation tells us nothing. The second variation criterion tells us nothing. We need to compute a higher order variation in order to make a conclusion. So for example, the third order variation we find to be this. At x1 star, corresponding to the critical load, it's not 0. So the third variation is not 0 at the critical load. Automatically then we're in the indefinite case where we have instability by Chitaev's theorem, and that's confirmed by the phase trajectory. So this kind of example is intended to make you comfortable with the conclusions we've drawn without doing any dynamics. Simple, trivial examples that illustrate the theorems nicely. I think Professor Luongo told us about this example where we have a rod, a rigid rod, with an angular restoring moment. So this is a rotational spring. The rod is length L, and we prescribe a dead force, which is a configuration-independent force. And this we can easily show is a conservative problem. The power of the force looks like this. Theta is the configuration. And we can easily integrate this to prove that then this power is expressible as the derivative of some energy. So there's a potential energy for this problem, and here it is. And we include now the spring energy. Okay. And equilibria, of course, are just the values of theta that render the potential energy stationary. And so they're the roots of this equation where F is the assigned force. Okay? And we see, of course, that theta equals 0 is an equilibrium configuration for all values of the force. So the straight configuration is always in equilibrium. We're interested in whether that equilibrium is stable or not. We can also find other equilibria for sine theta not 0. Then we can compute the equilibrium force theta relationship. This is the relationship. This is the force we must assign to maintain equilibrium at a certain value of theta, and that's this. Okay. So as theta tends to 0, this approaches the value mu over L. So there's an equilibrium always at all values of the force at theta equals 0, and then another branch of equilibria when the force reaches mu over L. And the force relationship looks like this. So here's our theta equals 0 configuration in equilibrium at all values of the force. And at values of force above mu over L, we have another branch of equilibria emerging. Below mu over L, theta equals 0 is the only equilibrium available above mu over L. To pick any value, say f star above mu over L, there'll be two equilibria associated with that. Say theta star and minus theta star. So there's a bifurcation of equilibria, and because of the shape of the curve, it's called a pitchfork bifurcation. And that occurs at mu over L. We can compute the second variation at any at any configuration, not necessarily in equilibrium, and we find this. At theta equals 0, the second variation becomes this, simply. And this will then be positive for the force lower than mu over L, which is the bifurcation point. Right? So these equilibria are all positive, or the second variation is strictly positive. So we have stability of that configuration, provided the force is small enough. And for f larger than mu over L, of course, the second variation is strictly negative. So we have instability of all the equilibria, of this equilibrium when the force is above this bifurcation value. Instability. Right. Let's see. We have the second variation being 0 there. The third variation is also 0 there, so we need to go to the fourth variation, which we find to be strictly positive at theta equals 0. So actually the theta equals 0 configuration is actually stable at the critical load. Okay? Again, we can express the first variation of the energy for any theta in terms of the equilibrium value of the force required to maintain equilibrium at that theta, which we've already computed. And this is convenient now because we can compute the second variation in this way. If the configuration theta is equilibrated, then this bracket is equal to 0. Okay? And the behavior of the system is controlled by the behavior of the equilibrium force theta relationship. So the second variation will be strictly positive at equilibria, say at plus minus theta star less than pi. So the second branch of equilibria on this curve of the pitchfork, these are always stable. Okay? And this is called the supercritical pitchfork. So you could say this is a safe bifurcation in which the configuration theta equals 0 is stable at the critical load, and any alternative equilibrium is also stable. To look at the dynamics, we have to introduce a kinetic energy. So it'll be some quadratic form involving theta dot. So we can put a mass at some distance, for example, from the origin, and compute the energy explicitly in terms of the theta dot squared. Lagrange's equations, like so. The conserved Hamiltonian, and so we can plot the phase trajectories. And so, for example, for the force above the critical load, theta equals 0, we would find is unstable according to purely from the dynamical perspective. And the two alternative equilibria are stable. Okay, so this again gives us some comfort that these criteria we've been using are meaningful in terms of dynamics. So let's keep the same rod that we had before, but now use a conventional spring, which is free to slide up and down such that the spring is always horizontal. okay? And prescribe the same dead force as before. And suppose the spring is relaxed when this is vertical. Potential energy, we can write the force contribution as before, and then the spring contribution. Equilibria, render the first variation 0, of course. And we can use that to generate equilibrium F theta relationship. Theta equals 0 is always a solution. The vertical configuration is always in equilibrium. And we can examine its stability by looking at the second variation. At 0, then we have a positive result when the force is less than KL. That gives us stability of the straight configuration, or the vertical configuration. When F is above KL, we have instability, etc. When theta is not 0, we can solve this as well to obtain an equilibrium force theta relationship, which approaches KL when theta tends to 0. So we have a bifurcation of equilibria, in fact, at the critical load as before. And we can write the first and second variations in terms of that equilibrium F theta relationship, evaluated at equilibrium, and we have the second variation now strictly negative on these alternative equilibria. And let's see. Yeah, so this is our relationship, the force theta relationship, which we plot here. Second variation will be always negative on this branch, so we have an instability at the of the alternative equilibria, and the system effectively collapses. That's called the subcritical pitchfork bifurcation. And now let's have the same problem as before, but just change the spring configuration slightly in this way. This is more interesting than the previous two. It combines features of the previous two problems. The spring, we'll say, is relaxed when this rod is vertical. We can compute the potential energy, the contribution from the force as before, and now the spring energy, like so. Look at equilibria, the places where the first variation is 0. We can then solve for the force in terms of the configuration. And theta equals 0, it's difficult to see maybe, is always in equilibrium. It is always a solution to this problem, no matter what the force is. And we can look at the case when theta is not 0 and compute an equilibrium force theta relationship. And let's see, that as theta tends to 0, that goes to KL over 2, if I've done it correctly. And now we would like to look at the second variation. We can write the first variation in this way. The second variation at equilibrium will involve the shape of this equilibrium force configuration relationship. So we'd like to know what that is. This is a complicated function, and if I've done this correctly, the limit of it has a negative slope as you approach theta equals 0. So at least with theta small enough, you can prove then that the second variation is strictly negative for positive theta and strictly positive for negative theta. So we have this kind of situation here. So if our perturbation involves a theta to the right of the origin, then that will grow in time. That will be unstable because the second variation is strictly negative. If the perturbation is to the left, then we can stay in a sufficiently small neighborhood of the equilibrium. We have stability in that case, but we have conditional stability because a perturbation on the other side will become unstable. So that's maybe understandable from the original diagram. A perturbation in which, as shown here, will be unstable. So you have the configuration, the vertical configuration. A perturbation like this will be unstable, cause a collapse. A perturbation to the left will compress the spring, which will be resisted by the spring, and that will be a stable situation. And that case is called the so-called transcritical bifurcation. Okay, so just some very simple examples to illustrate Lyapunov and Chitaev theorems. We'd like to know, how are these theorems changed by the presence of dissipation, or is there any qualitative change in the conclusions? So let's add dissipative forces to our conservative forces. And we'll stay in the autonomous case where these are not explicitly dependent on time. So this is, you might say, the classical or perhaps even uninteresting case where we do not supply an explicit time-dependent forcing function. This could be just damping due to dissipation in the system, inherent to the system. If we look at our Hamiltonian again, we would find from the equations of motion that that's equal to this. We've seen that before. And we'll call this the dissipation, like so. It's the power of the non-conservative forces in this case. And we'll suppose those forces vanish whenever the velocity vanishes, and are such as to make the dissipation negative definite. So this is the typical case with damping in the system. So the dissipation is negative definite, and that guarantees that the Hamiltonian, or the total energy, is always decreasing on any trajectory of the dynamics of the system. What we can actually do in this case is prove asymptotic stability of the system, provided the system is stable. So if, suppose our state is stable, in other words, suppose the conditions of the Lagrange-Dirichlet, or if you like, the Lyapunov theorem, are satisfied. So for example, we had E positive definite in a neighborhood of the origin. Okay, so then the Hamiltonian, there's a candidate Lyapunov function. We showed before that the Hamiltonian, the total energy, is a Lyapunov function. And its time derivative then, just from the dynamics, is just that of the Hamiltonian, therefore never positive. And then we can actually show that the origin, the equilibrium, is asymptotically stable. So we start out with stability, and now we want to show that we don't disturb that conclusion. In fact, we improve it. We show asymptotic stability. So stability means we have the trajectory within some neighborhood of the origin, which means the configuration and the velocities are both in the same, bounded by the same number. Okay. We need a little bit more in order to prove our theorem, however. Maybe perhaps unexpected, but at least this particular proof requires more stringent conditions. We're going to suppose that there is no equilibrium point Q hat in the K neighborhood of the origin. And we can guarantee this by imposing the requirement that the derivatives of the energy should be non-zero when Q is non-zero. Because otherwise, if there were such a configuration, Lagrange's equations would give us this, and we're supposing that when there's no velocity, there's no dissipation either. So we would have a stationary energy at such non-zero points, Q hat. So we can forbid this behavior by simply demanding that there should be no other stationary points of the energy in this ball except the origin. In other words, the origin is an isolated equilibrium configuration. Okay. Looking at the autonomous case, the forces don't depend explicitly on time, so we can write this as a first-order autonomous system. We would like the property of a unique solution. There's a classical theorem which guarantees this. For example, if the right-hand side satisfies a Lipschitz condition. And this also ensures that the configuration, or the trajectory, depends continuously on the initial data in this way. And this will be an ingredient of our proof. Because we have an autonomous system, that means that if you have a trajectory starting at time at configuration x naught, if you shift the time scale, like so, by some constant t1, then these two solutions xt and x tau lie on the same trajectory. Okay? So you could think of this solution as simply the continuation of the solution x tau emanating from x naught is the same as xt emanating from x1, where x1 is just x tau at time at t1 when t is 0. Okay. And so from the uniqueness result we have that x at t plus t1 emanating from x naught is the same as x at t emanating from x1, okay, where x1 is just the original solution at t1 emanating from x naught. That turns out to be important. Okay, so let's consider a trajectory emanating from x naught. So that means a certain initial configuration and initial velocity. And because we already have stability by virtue of the Lyapunov theorem, that means we have bounded q of t and q dot. So if we consider a sequence of instants tending to infinity, when we generate an associated sequence of configurations, qn, which are just the q's at each of these discrete times, and associated velocities, and these will be bounded by virtue of stability. So we can invoke the so-called Bolzano-Weierstrass theorem to claim that since these are bounded sequences, they have convergent subsequences, and say they converge to q star, q dot star. If hk is the associated value of the Hamiltonian at, say, the kth member of the sequence, and h infinity is h at q star, the limit of the sequence, the subsequence, then by continuity of h, the sequence of h's converges to h infinity. Okay. And also h is non-increasing, so it has to be less than its initial value. And it's, under our hypotheses, it's never negative either. Okay. So we're going to make an assumption that leads to a contradiction. Maybe I'll restate it here. So this is simply a restatement of the same argument. You have a bounded infinite sequence. So there's a convergent subsequence. X star, let's say, is the limit of the state, and the limit of the sequence of associated Hamiltonians converge then to the Hamiltonian evaluated at the limit because of continuity of h. And we have initially, because at some x naught we have the initial Hamiltonian strictly positive. Its time derivative is non-positive, so the Hamiltonian itself is bounded and monotonically non-decreasing. It looks like this in time. So this sequence of Hamiltonians will converge as well to h infinity. Let's see, that's the Hamiltonian at x star. So here's where we'll make an assumption that leads to a contradiction. Suppose that the limit of that sequence generates a Hamiltonian that's strictly positive. Then, because this Hamiltonian is positive definite, x star is not 0. So x star is not an equilibrium point by our hypotheses, right? So remember, we assume that there's an isolated equilibrium at x equals 0. So let's consider a trajectory beginning at this limit, x star. Call it x hat. So that means that the dissipation will be strictly negative for some interval of time, because x star is not an equilibrium. So the system evolves and dissipates energy. So at any subsequent time, the Hamiltonian will be strictly less than h infinity. Okay? That's a consequence of our assumption. Okay, so let's consider a trajectory beginning at, say, an element of the sequence that we were talking about. That sequence converges to X star, a subsequence. And because of continuous dependence on the data, we assumed this Lipschitz condition, the configuration emanating from YK will converge to the configuration emanating from X star as YK converges to X star. That means the sequence of Hamiltonians will converge as well by continuity. And because H at X star, H on the trajectory emanating from X star is strictly less than its initial value, which was H infinity then, for K large enough, we can guarantee that the Hamiltonian emanating from the kth element of the sequence is also strictly less than H infinity. So here's our trajectory emanating from YK, the kth element of the sequence, and because of the autonomous nature of the problem, that's simply the continuation of the solution emanating from X naught, let's say, in terms of tau. Okay. So we concluded now that because of this property, the uniqueness property, this is equal to this, that H at some subsequent time is less than H infinity. And that's impossible, right? So that's the contradiction. So the supposition must be wrong, and so H infinity is 0. In other words, the limit of the Hamiltonian at large time for trajectories emanating at X naught has to be 0. Since this is positive definite, then the norm has to tend to 0 as well, so the trajectories will return back to the origin, and that's asymptotic stability. So if you have stability and you add damping to the system, as you would expect physically, you do not disturb the stability conclusion. Okay, so perhaps a more interesting question is, does dissipation alter the conclusion with respect to instability? And you'd think that would be a well-studied problem, but it seems not to be discussed, at least in the monograph literature. There's a nice paper by Koiter a long time ago, depending on how old you are, this may or may not be a long time ago, on the instability of equilibrium in the absence of a minimum of the potential energy. So he's looking at the indefinite case, which generates instability according to the Chitaev theorem. And the question is, can dissipation alter that conclusion? And the answer is no, ultimately, but it's interesting. What's interesting about this paper and many of Koiter's papers is there's no mathematics in them whatsoever. It's simply a written discussion of the proof. And so one has to actually fill in the mathematical detail. And as always, he's right, but one needs to convince oneself of that. So we'll suppose we have, to set this up, let's suppose that our energy is continuous, so if it's k times differentiable, then it will ultimately be continuous. Let's suppose all the variations up to order k minus 1 are 0. So that the energy looks like this then, with some remainder. We can use the homogeneity of the kth variation to write that this way. And this is the unit, U lives on a unit sphere, as before. And this is simply what we had before. The remainder is a continuous function of Q that vanishes at 0. And now we'll suppose that we have the indefinite case, as Koiter hypothesized. The negative definite case will be a special case of this then. So we can guarantee that in the absence of dissipation, the equilibrium is unstable, as we've seen that before. Okay, so somewhere on the unit sphere then, there will be a point where the kth variation is negative, and this is a continuous function on the unit sphere, so this function assumes its minimum value. Let's call it m sub k, which will then be strictly negative. And then we can construct a cone, as we did before, where the kth variation at the configuration q is again strictly negative by virtue of the homogeneity of the kth variation. Okay. So let's pick a point U in this set where the kth variation is negative on the unit sphere, and pick norm Q small enough so that we can make a bound on the remainder function. Right? We're guaranteed to be able to do that because this is a continuous function of Q. So this is some fixed number, and we can make Q small enough to make this true for any such fixed number. And suppose alpha k is less than 1, we can certainly find a Q small enough to achieve this inequality. Then the energy, which is this, or modulo norm Q to the power k in the denominator, looks like this, and we can bound that above by some constant strictly negative times this number. If we look at what we had before, then the energy will be less than some strictly negative number for Q non-zero in this ball. The energy itself, not just the variation. So if we have Q in this cone sufficiently close to the origin, we have the potential energy strictly negative. Elsewhere, we have the opposite. Okay? So the cone can consist of a number of sectors. It's just that outside this cone we have E non-negative. Let's see. Let's consider a punctured region C1, which is that ball, intersection that cone, but take away the origin. So it's this cone minus the origin. So the potential energy then will be strictly negative in this C1 minus the origin. Okay. So E is continuous on this compact set, this ball. So its minimum will be achieved in that set, and it's strictly negative because of the existence of such Q. Okay. We'll suppose now, as before, that there are no equilibria in C1. That is, the origin is an isolated equilibrium. We guarantee that by imposing this condition. This could never be zero except at the origin. So suppose we have a system with that property. So that means as long as Q of t, the trajectory remains in C1, the velocity cannot vanish over an interval of time identically. If it did, there would be equilibria, and we're excluding that. So that means the dissipation is strictly negative or in an interval of time. Let's see. And there are no equilibria outside this sector that have energy less than that at the origin, namely zero. Let's see what's interesting here. So let's pick we can't control the perturbations, so let's pick an initial condition inside this C1 minus the origin. So the energy, the initial value of the potential energy is then strictly negative. And therefore the Hamiltonian at that state, at that equilibrium state, is strictly negative. Let's pick an initial velocity now, not shown on this diagram. So small in norm that h at that initial condition is strictly negative. That's possible because h is a continuous function of q and q dot. Okay? And it's strictly negative at q dot 0. So since q of t is a continuous trajectory under our assumptions, that means there's an interval of time in which the trajectory stays in that sector C1. And the dissipation is strictly negative because there are no equilibria, so there are no the system will not stay at a particular point over an interval of time because there are no other equilibria under our assumptions. So the Hamiltonian will continue to decrease. This will be a strictly decreasing function. So let's make an assumption that will generate a contradiction. Let's assume that the configuration stays in a ball surrounding the origin. In other words, let's assume stability. Then, because h has continued to decrease, and the potential energy starts out with a negative value, the configuration must stay in the sector where the potential energy is negative. But then as long as it does that, the total energy, the Hamiltonian, decreases without bound. The kinetic energy, of course, is non-negative, and so that forces the potential energy itself to decrease without bound. That means there has to be a time such that it becomes less than its minimum value inside that compact set. And of course, that's a contradiction. So that means that there must be a time at which the trajectory does not remain in that neighborhood of the origin. And that proves the instability. So dissipation does not alter the conclusions with respect to instability, although we need a few more hypotheses to make that conclusion. Okay, the next thing I want to talk about is linear approximations, and we've heard more about these from Professor Longo, and I expect we will again, so I'll give a very rough sketch. Often it's hard to find a Lyapunov function for a general system, and perhaps even harder to find a Chateau function. For mechanics, we've been lucky in identifying the energy as a Lyapunov function, and certain combinations of the energy as Chateau functions. But for a general system, that's a difficult task. There's no systematic way of generating such functions. So one is left then with studying the actual dynamics, and one would like to approximate the system in some way, for example, through linearization. So suppose we have a system that admits 0 as an equilibrium, and we'd like to linearize the system about that equilibrium point. So if we have a smooth or a differentiable right-hand side, then we can establish a linear part and a remainder, just using Taylor's theorem with remainder, literally. So this is an exact expression. G is just this. We add and subtract the Aij, and this is the same system. And G, of course, then will be continuous and vanish at the origin, which means this part is small o norm x. In other words, we're assuming the system admits of linearization, like so. Okay. So let's just study the linear part of the system, x dot equal ax. And solutions, we'll have solutions of exponential type like so. And these eigenvalues, these will be then eigenvalues of A and eigenvector C, which is the mode of this trajectory. Okay, so there'll be n, this is an n by n matrix for an nth order system. We'll have an nth order polynomial with real coefficients in our case, and C are the associated eigenvectors. And so there are n roots, lambda, real or complex, and because the polynomial that generates them has real coefficients, if they're complex, they'll occur in conjugate pairs. And then we can construct the solution via superposition for our linear system. And this will be so, the structure will maintain if the eigenvalues are distinct. If they're not, then we'll have something else. So for example, suppose the first eigenvalue has multiplicity m1, the second one has multiplicity m2, etc. And where all the multiplicities add up to the order of the system. Then it's possible to show that the general solution looks like this, with some polynomial dependence on time and the exponential term with some fixed vectors. And just from the structure of the solution then, you can see if the real parts of all the eigenvalues are strictly negative, then this trajectory will decay to 0 asymptotically in time. However, if there's one real part, if even one eigenvalue has a strictly positive real part, then that will explode in time, and the origin is unstable. So that's the conclusion for the linear system. The interesting thing is to see what it implies for the nonlinear system. So some simple examples I won't bother you with. Just very simple examples. We're interested in the nonlinear problem and the extent to which information about the linear problem can inform us about the nonlinear problem. This is a large literature, and it would be better discussed, I think, by Professor Luongo than I'm going to do here. The two main results I want to mention is that if all eigenvalues of A have strictly negative real part, so that the zero solution of the linear system is stable, then the zero solution of the nonlinear problem is also stable, at least conditionally, when the initial condition is sufficiently close to the origin. And we will prove it via Lyapunov's theorem. The second main result is if there's an eigenvalue, if there's one eigenvalue, at least, with positive real part, then the zero solution of the nonlinear problem is unstable. Unfortunately, these do not address what we have called the critical case, as in a critical load, for a conservative system. In the critical case, it turns out, we will see in a moment, is that all real parts of eigenvalues are non-positive, but at least one of them is equal to 0. So this does not fit into either of these two theorems. And in this case, we have no information from the linearized system alone. Or perhaps we can do more. So here's an example of a two-dimensional system with an obvious linearization, x dot equals y, y dot equals minus x, and then the nonlinear part. The linearization has a matrix A like so, purely imaginary eigenvalues. And the real parts are 0, which fits into this alternative, which is not addressed by these two principal results. So the linear system can tell us nothing, by itself can tell us nothing about the stability of the zero solution to this nonlinear system. Nevertheless, we can show that for this same system, this is a Lyapunov function. So, in fact, the origin is stable. So let's have a sketch of the first theorem. And I'll just work in two dimensions because it's easier to see the structure of the theorem. And it's possible to generalize this. So the basic idea is to construct a Lyapunov function for the linear system. And then show that the same function is also a Lyapunov function for the real system, provided norm x is small enough. And that guarantees the conditional stability. That is, if the initial condition is sufficiently close to the origin, then the nonlinear problem will be stable. So in two dimensions, A looks like this, let's say. And we need to find the eigenvalues, which is this quadratic equation. P is the trace of the matrix, Q is the determinant, and then the eigenvalues are these two. And we can distinguish various cases depending on the sign of the discriminant. So we'll look at three cases. Discriminant equals 0. Then we're going to have stability. Let's see, the eigenvalues are real, and so the eigenvalues are equal to their real parts, both the same. And of course then will be strictly negative if and only if P is strictly negative. So the linear problem in that case predicts stability. If the discriminant is negative, then we have complex roots, but again, the real parts are the same, and we'll have stability if and only if that one real part is strictly negative. The alternative, the discriminant is positive, generates two subcases, and let's see. These two subcases both correspond to negative real part. And so again, when these conditions are satisfied, we'll again have stability. So basically what we can conclude is that the entire system, the linear system, will be stable whenever the trace is strictly negative and the determinant is strictly positive. So we'll assume henceforth that the linear system yields stability so that we have these conditions satisfied by the parameters in the problem. And we'll impose these henceforth to guarantee stability of the linear problem. So the idea is to construct a Lyapunov function now for the linear system. And the easy thing to do is to construct a quadratic function, if possible. with some symmetric matrix K. So we want K to be positive definite to ensure that V satisfies the conditions of a Lyapunov function, but its derivative should be negative on any trajectory of the system, the linear system. So V dot then satisfies this on any trajectory. So we would like this matrix A transpose K plus Ka, where K is to be constructed, A comes from the linear system, we would like that to be negative definite. In particular, the easy thing to do, if possible, is to arrange it so that it's minus the identity that guarantees V dot is negative definite. In fact, in 2 dimensions, here's a solution. To my knowledge, this does not extend to n dimensions, but nevertheless, we can find parameters m and n such that this will satisfy our criteria. And here's the solution. For these values of the parameters, remember p is strictly negative in our case, q is strictly positive. For these values of the parameters, we have such a k that fulfills all our requirements. And then we can show, in this case, that we do indeed have a Lyapunov function for the linear problem. So now we study the nonlinear problem and ask, can the same function then be a Lyapunov function for this problem? We've already constructed V, but V dot now will depend on the dynamics of the nonlinear problem. So we insert that here, and we'll have these extra terms coming from the nonlinearity. And we can apply, say, Cauchy-Schwarz inequality to those terms. Perhaps you've all heard about the matrix norm, defined this way. Supremum for non-zero x of ax over norm ax over x. So in particular then, at any y, the norm of ay is bounded above by this norm times the norm of y. It's convenient to normalize the argument, and then we write ax as a times norm xu, use linearity to write that as norm x au. So norm ax is just norm x norm au, and so if we put that in this definition, that's equivalent to saying that this matrix norm is the supremum of au norm on the unit sphere. Okay? And then we can easily see that this is simply the maximum eigenvalue of A. And so this will always be bounded, of course. And in finite dimensions, linear operators are always bounded, in this case, by the maximum eigenvalue of A, which characterizes the linear part of the system. So V dot, the time derivative of our, hopefully, our Lyapunov function, looks like this. You can see immediately that because of the nonlinearity, we can make this smaller than this, and so the behavior will be dominated by this leading term. That's easy to do. So, using Cauchy-Schwarz and the matrix norm. So we can make norm x small enough to guarantee that V dot is negative definite. And so we have a stability of the origin in that case. So that shows that that establishes theorem 1 at least for 2-dimensional problems, which are easier to illustrate. Let's look at theorem 2, which is the case when at least one eigenvalue has a positive real part. The linear system is unstable. The origin is unstable in the linear system. We'd like to know if the same is true for the nonlinear system. Let's consider just some particular cases just to illustrate. Suppose A has distinct real eigenvalues, one positive, one negative, so that we're in the case of theorem 2. We'd like to diagonalize the system if at all possible for the purpose of constructing a Chitaev function. So let's introduce a transformation C, a non-singular transformation, which defines a new variable u. And so our system, our linear system, is then equivalent to this. And we can choose C so as to diagonalize this combination here, even though A is not symmetric in general. And for example, for B not 0, which is one of the elements of A, here is such a C. For B equals 0 but C not 0, here is such a C. And when both are 0, of course, the identity will do it. So then our original linear system is equivalent to this with a diagonal D. And we can show that this is a Chateau function in this case. Remember, lambda 1 is positive, lambda 2 is negative. So if we graph this, we have behavior like so. U positive here, U positive here. This is the shaded region is the region U plus in Chateau's theorem. It includes the origin. And now we simply have to show that U is an increasing function in that region U plus on the dynamics of the system. The D is symmetric, so this gives us the identity here twice. And we simply have something that's positive then everywhere, and therefore in the sector U plus. And so we have instability of equilibrium in this case using Chateau's theorem alone. So, well, let's see, that's the linear problem. We can then do an estimate of G for the nonlinear problem, again using matrix norm and Cauchy-Schwarz, etc., and the continuity of G at the origin. So if we make norm x small enough, then the behavior of U dot will be dominated by this positive definite part, which means we can force the trajectory to leave a sufficiently small neighborhood of the origin, and we have instability. Another simple case in 2 dimensions. Suppose you have complex roots, so they look like this, and the real part is positive. One can construct, given the linear system, the matrix A, one can construct a G, an invertible G, to achieve this form in terms of these real and imaginary parts of the eigenvalues. For example, this G accomplishes the transformation that we need, where C is as before in the earlier problem. Then we can make our linear system equivalent to this linear system, and we can show that this is a Chateau function. This is a positive definite function, and for the linear system, its derivative on any trajectory is also positive definite. So the origin is unstable, and it's easy to do the required estimates then to show that the same is true for the nonlinear system, provided norm U is small enough. So again, we have instability in that case. Okay, so just a few simple classical results. We could easily make them more general in the classical framework to connect stability or instability to the behavior of the linearized problem. So that suggests, if we're doing mechanics, that we should look at the linearization of Lagrange's equations and connect the behavior of the linearized system to our stability and instability theorems. So let's first look at the conservative case, which we've been doing up till now. Lagrange's equations look like this, the Lagrangian, etc. So explicitly, if we work out this derivative, Lagrange's equations are like so in terms of the accelerations, generalized accelerations. So suppose we have an equilibrium configuration Q sub E, and we're going to linearize the system about this equilibrium state. So any perturbation of the equilibrium, Q of t minus Q equilibrium, we'll write it in this form in terms of something that has, say, a function which together with its derivatives, say, is order 1 for all time, by assumption. And the size then of this perturbation will control by epsilon, which is a very small number. And then the idea is to retain the leading order terms in this equation in terms of epsilon. So let's expand various terms in the equation, the LDQ, for example, the 0th order term, the linear term, order epsilon, and then small o epsilon, the nonlinear terms. The remaining terms in the equation are already order epsilon, right? Because, for example, Q dot is of order epsilon, Q double dot is of order epsilon, whereas Q is of order 1, right? So we have an order 1 term here. And U is not a unit vector as it was before. It's simply a way of encoding information about the perturbation. Let's see. So dl dq at 0, of course, is just 0, because from the expression for the kinetic energy, if we take a q derivative, we still have velocities, but at epsilon equals 0, there's no velocity, so this vanishes. And we just have the e dq, but that's 0 because the QE is equilibrated. Okay? So the entire thing starts at order epsilon. So we substitute the expansions into the nonlinear equation, divide the equation through by epsilon, and simply pass to the limit of formal exercise. Pass to the limit, and we achieve the linearization of the Lagrange equations like so, where the subscript 0 means evaluation at the equilibrium configuration. Okay? This term is simply the mass matrix at the equilibrium configuration. Well, in general, and evaluated at the equilibrium configuration. This is a collection of numbers. We call it the mass matrix. Okay? So it's the mass matrix at equilibrium. And of course it's symmetric, and it must be positive definite because the kinetic energy is always a positive definite function of the velocities. These other terms, these mixed derivatives, are like so. But at epsilon equals 0, there's no velocity, so they vanish at epsilon equals 0. So we have no, in other words, we have no damping term because we have no damping in the system. The remaining derivatives that are of any interest are these, and this is just the stiffness, ultimately. Again, we have this expression for the q derivative of the kinetic energy, but at epsilon equals 0, these vanish, and we're just left with these, which we called before the stiffness matrix. So the linearization can be put into this form, which is familiar to people who do structural dynamics. A positive mass matrix, then the acceleration, some stiffness matrix times the linearized configuration, the linearized perturbation in the configuration, and this is the linear equation of motion, linearized about our equilibrium state. So, as usual, we try solutions of exponential type. This is a constant coefficient system, and lambda squared then must be an eigenvalue. V must be an eigenvector of this combination. Okay? And so to have a non-zero perturbation, we must have a 0 value of this determinant that generates an nth degree polynomial in lambda squared. Results that are well known in vibration analysis. You can show that the lambda squares are all real. That's the same as the usual proof in matrix theory. And you can show that the associated eigenvectors, I won't waste time on this, are orthonormal with respect to the mass matrix, or at least orthogonal with respect to the mass matrix. So for example, if you have two eigenvectors, they satisfy this zero inner product, two eigenvectors via the mass matrix. Okay? So we have real squared eigenvalues and mode vectors that satisfy this orthogonality condition. Because of the positivity of the mass matrix, we can always normalize those eigenvectors to require this. So I won't spend any time on that. And there are always n such eigenvectors, and whether or not the eigenvalues, the squared eigenvalues, are distinct. And we can show that they form a linearly independent set, and that's useful later. To see that, let's make a linear combination of these equal to 0. And then take an inner product with one of the mode vectors. So this bracket here is 0. And then use linearity, and we have this. And then we have this orthonormality condition with respect to the mass matrix. So this is the Kronecker delta kj. And of course, then we just get a sub k. So the only way this can be true is if all the coefficients are 0, so the v's are linearly independent. and they span this n-dimensional space. We can use them to generate a very nice representation due to Weierstrass in terms of so-called normal coordinates. Let's write our solution, our linearized solution, in terms of these eigenvectors, right, which span Rn. Use them as a basis. These are fixed eigenvectors. And write the motion then in terms of this representation. And then substitute into the equations of motion, like so. And then take an inner product with a particular eigenvector, Vi. So we'll have to get 0, of course. And then use the orthonormality with respect to the mass matrix, and we have this. For each eigenvector, Vj, we have this property because of the equation of motion. So we can use that in this term. The inner product here then gives us this combination, and this again, these are orthonormal, so we get this. What that means is that if we take an inner product of the equation of motion with the particular eigenvector, we decouple the equations entirely. Each mode is decoupled, so this is well known in vibration analysis. Each mode is entirely decoupled. And whenever lambda squared is not 0, we get purely exponential solutions. I've read somewhere in the literature that Lagrange believed that there could be some secular terms as well, but if you put the problem into normal coordinates like this, in fact there are only purely exponential solutions whenever the squared eigenvalues are non-zero. When they're equal to 0, if you have some that are equal to 0, then you just get linear behavior in time for those particular eigenvalues. This is what I was looking for. Okay. So just to sketch, we can convert the linear equation of motion. M is positive definite symmetric, so it has a positive definite symmetric square root, and we can use it to define a variable z, right? One-to-one relationship, and then rewrite the equation in terms of z, which will look like this then. So we isolate the second derivative in terms of a symmetric matrix, and then the eigenvalue problem can be written this way. From this you can see all the lambda squares will be real. This is the standard eigenvalue problem. And immediately you see also the associated eigenvectors will be orthonormal. And then if we, in terms of the original physical displacement u, we then have the representation we had before, where our v that we had before is just this inverse of the symmetric square root of m times x. So this orthonormality condition reduces to the one I claimed a moment ago. But the actual mode vectors are orthonormal or orthogonal with respect to the mass. Okay. So for any eigenvector, non-zero, of course, we can compute, if we have that eigenvector, we can compute the associated lambda squared, the eigenvalue for that particular eigenvector. So let's consider some cases. Suppose S is positive definite. So this ratio is strictly positive. Then every eigenvalue every squared eigenvalue is strictly negative. So the eigenvalues are pure imaginary. And this is the inconclusive case according to our linearization theorems. We have no real part of the eigenvalues. So the procedure of linearization alone is inconclusive, but this actually is the typical case, right? This is the case of, we know that in this case we have a positive definite second variation at equilibrium. So the Lagrange-Dirichlet or Lyapunov theorem ensures the stability of equilibrium in this case. What's interesting is that a purely linear analysis without appeal to such a theorem, without appeal to the energy argument, tells us nothing in this standard case, because the eigenvalues have no real part. This is just pure oscillations. Okay. some facts. So the stiffness matrix has n real eigenvalues, right? This is a symmetric matrix. And of course the n eigenvectors, and we can normalize them, and they're all orthogonal to each other. There exist n such eigenvectors. For each one of them we have this, where s is the associated eigenvalue. And suppose we name our departure from equilibrium, this is our perturbation, call it A. We can use that set of eigenvectors as a basis, the set of eigenvectors of S, not the original V's that we talked about, but rather just the eigenvectors of S, and decompose this perturbation in that eigenbasis. And then the second variation, evaluated at this perturbation, can be written this way, where SA has this representation because each E is an eigenvector. So we have this representation of the second variation in terms of the eigenvalues of S. And A is the perturbation, and the E's are the eigenvectors of S. Okay? So these are, of course, inner products. These are the projections of A onto the basis elements. So let's suppose that, let's look now at the second possibility. We first looked at the case when S is positive definite. We know, at least from the Lagrange-Dirichlet theorem, that we have stability. Linearization tells us nothing. So that at least is an incentive, perhaps, to study these Lyapunov-type theorems. Suppose S has a negative eigenvalue, at least one. That means the second variation is indefinite, or possibly negative definite, if they're all negative. Then we know from Chataev's theorem that the equilibrium is unstable. We would like to assess this question without knowing this theorem, simply from the linearization of the problem. So suppose we have one negative eigenvalue and let E be the associated eigenvector of S. Sorry for the messy writing. Now our mode vectors are linearly independent. They're a form of basis, so we can expand that eigenvector of S in that basis. And there is these are at least one of these is not zero. Right? These are all real numbers, and they're not all zero. S on E then looks like this, but SVJ from the equation of motion is just this. And so the eigenvalue itself, which is the projection of the eigenvector onto SE, looks like so. And this inner product we can work out by decomposing E in the mode basis, using linearity. We can write that this way, and we have this orthonormality condition. So these projections are just the coefficients of this eigenvector in that basis. So S is minus alpha j squared, again, times lambda j squared. And if S is negative, well, the absolute value of S, of course, is strictly positive. At least one of these alphas is non-zero. So at least one of the lambda squares has to be strictly positive in order to achieve this condition. We have at least one strictly negative eigenvalue of S, the indefinite case. At least one lambda squared has to be strictly positive, which means there's a lambda with the positive real part. And linearization alone now is conclusive in this case. Linearization predicts instability, and that comports with the Chataev theorem because we're in the indefinite case. Here's the typical situation, which is neither of those. In a typical situation, say we have a force which may depend on a parameter, and as we control that parameter, say P, we generate a sequence of equilibria that are parameterized by P. Right? So each of these is an equilibrium state. And the typical situation is, at any value of the parameter, the associated stiffness matrix for the linearized problem, linearized about any such equilibrium state, is positive definite. So the second variation is positive on this path of equilibria, and so we have stability of each point on that path. In the typical situation which we saw, for example, in this snap-through problem that we looked at, that conforms to this case. There'll be a value of the parameter at which the second variation ceases to be positive definite. So the stiffness matrix associated with the linearized problem ceases to be positive definite. In other words, there is a particular vector A, call it A star, non-zero, which gives this condition here, which gives equality. Okay? And this is, we'll see, this corresponds to the indefinite case. So we no longer have a positive definite second variation, and we need further analysis. To do that, let's use the orthonormal eigenvectors of the stiffness matrix at that state with eigenvalues Si. So we can decompose that particular mode, A star, that we were talking about. There's an A star not zero that nullifies the second variation. We can decompose that in the eigenbasis and then write SA star using the fact that E is an eigenbasis. So we have eigenvalues, eigenbasis. And then we compose this quadratic form. There's an A star that nullifies this quadratic form. That's the typical case we're looking at. And so then we have this representation. Okay? And because A star is not zero by hypothesis, at least one of these projections onto the eigenbasis must be non-zero. Okay? And the situation we're in is that all of the eigenvalues are non-negative. One of them, or some of them, may be zero. In particular, this equality here proves that if there's an eigenvector for which this inner product is non-zero, then this associated square is strictly positive, then the coefficient eigenvalue must be zero whenever this is true. Okay? And so this corresponds to, this forces the determinant of S to be zero. So that means for that A star, we again have this situation where any eigenvector which has a non-zero coefficient here, non-zero projection, A star makes a non-zero projection with that eigenvector, the associated eigenvalue must be zero from the previous line. So SA star has to be zero, which of course is weaker than saying that the second variation is zero. So A star must be a null eigenvector of the stiffness matrix. So this perturbation Q minus Q equilibrium, we call it A star, that's a surrogate for U of t, that satisfies the equation of motion with no acceleration. So it's a solution to the linearized equilibrium equation. So that we have an equilibrium Q, E, and if there's a non-zero solution to this equation, then we have an adjacent equilibrium configuration according to the linearized theory. So that's a bifurcation of the equilibrium at that point. So this configuration Q, which is QE plus this A star that solves this equation, is also an equilibrium configuration according to the linearized theory. Okay. So at the critical value of the load that causes this condition, this breakdown of the second variation, that also corresponds to non-uniqueness of equilibria in the conservative case. In other words, we have two equilibria at that particular load, or many equilibria at that particular load, right? Any null eigenvector of the stiffness matrix generates adjacent equilibria. Okay. So the breakdown of the second variation, when it ceases to be positive definite, that corresponds to a bifurcation of equilibrium according to the linear theory. And we've seen examples of this already, several. That's not possible for loads less than the critical value because the second variation is then positive definite and there can be no such mode, no A star, that generates an adjacent equilibrium. So we can say, in the next few minutes, the positivity of the second variation that guarantees the hypotheses of the Lagrange-Dirichlet theorem for conditional stability of the equilibrium. It also implies uniqueness of equilibrium according to the linearized theory. This is the indefinite, this is the case in which the dynamics alone, the linearization of the dynamics, yield no information. Linear theory by itself, the linear dynamical theory, tells us nothing, but nevertheless we can guarantee stability via Lagrange-Dirichlet or Lyapunov. Okay, so we could say then the presence of an adjacent equilibrium means that this cannot be satisfied. The second variation cannot be strictly positive. Although we don't know the behavior of the system without further analysis, we can say that there's now a possible or potential instability. So this is why engineers are concerned with conditions under which there exists an adjacent equilibrium, so-called buckling of the system. Because buckling could signal a potential, or signals a potential instability. We've already seen examples where this bifurcation, the system is stable at bifurcation, so it doesn't imply instability. But the existence of an adjacent equilibrium means that the second variation cannot be positive definite, so we might have an instability. So buckling theory by itself, the search for a buckling mode, doesn't guarantee instability by any means, right? Okay. The point here is that this buckling mode, call it A star, if you decompose it in the eigenvector basis of the stiffness matrix, the only non-zero terms here are those corresponding to zero eigenvalues of the stiffness matrix. These are called eigenmodes. And we can enumerate them, we can solve for them algebraically. So that means the adjacent equilibrium must be a linear combination of these so-called eigenmodes of the stiffness matrix. All the null eigenvectors of the stiffness matrix. Okay, if we remember that for any eigenvalue S of the stiffness matrix, we have this result where the alphas are the projections of the eigenvectors in the mode basis, the B's. And not all of them vanish, of course. And then we have this representation. In the case we're looking at, this critical case, at least one of these eigenvalues vanishes. So at least one of the lambdas must vanish. Lambda squares must vanish. And perhaps m of them do. And the remainder then must be strictly negative in our case. If you look at the associated normal modes corresponding to the vanishing squared eigenvalues, we just get linear behavior in time. Okay? And then the remaining part contribute purely oscillatory behavior of the system. So purely oscillatory behavior superimposed with a linear growth in time. So linear theory, if you took theory seriously, would predict that the perturbation is becoming unbounded for large enough time, in polynomial growth in time. But of course, this is by the time this happens, the nonlinear terms will become significant, and we can draw no conclusion at all in this case. Okay. So I simply wanted to make the point that pure dynamic analysis yields no information, at least if we linearize. The linear analysis yields no information. Okay. And also, unfortunately, in this situation, we do not know if we have the conditions of the Lagrange-Dirichlet or Lyapunov theorem satisfied, because the second variation is now ceases to be positive definite. Nor can we satisfy we're not sure if the conditions of Chataev's theorem are satisfied either, because we do not have the indefinite case either, where we have a configuration that renders the second variation negative. So we can draw no conclusion on the basis of the second variation, nor can we draw any conclusion based on purely linear analysis of the dynamics. So this is the case where we really must look at higher order variations. In other words, we have to do a weakly nonlinear analysis to assess the stability of the state at the bifurcation point or the adjacent equilibrium point. So if we can, for example, find a a third variation that's non-zero, we can guarantee instability, and we've seen that by some simple examples. Okay, so I think I have a moment, 10 minutes or so, do I? And let's quickly discuss the so-called non-conservative case. Here we can do nothing really using the energy theorems. We'll see why. There's simply no energy to discuss. In the non-conservative case, let's suppose we have some loading Q. The generalized forces depend on the configuration. Let's simplify matters by assuming this is a loading that depends only on the current state of the configuration. And we remember that the conservative case means that we can always evaluate the generalized forces as the gradients of some scalar, the potential energy. And so if these Q's are differentiable, E then would be twice differentiable, let's suppose that. And of course then this matrix, the matrix of derivatives, would be symmetric in that case. So a test for the absence, the failure of conservativeness is this condition here. If the derivatives of the generalized forces with respect to the configuration components, if that generates a non-symmetric matrix, then there can be no such E, and we call this the non-conservative case. And then we have to consider the Lagrange equations in their generality. Okay, so we don't have a Lagrangian, so to speak, anymore. We can still linearize the system, of course. The generalized forces, say, are 0 at equilibrium. And then we have the linear part, which is just the matrix of derivatives of the generalized forces. And in our case, these will not be symmetric anymore. And if we linearize the system as before, we'll have something like this, where now the coefficient matrix here is this non-symmetric matrix in general. And again, this admits exponential solutions. And the V's then must be eigenvectors, lambda squares must be eigenvalues. And we have this determinant equation. Because of the loss of symmetry of n, these roots will generally be complex now. So the solutions will look like this. Oscillations bounded by some exponential function. Right? And then we can have also, if we have repeated roots, we can have some also algebraic dependence. So when all real parts are strictly negative, we have conditional stability according to Theorem 1 for dynamical systems. If at least one real part is strictly positive, then we have instability. And so really we must make recourse to a dynamical analysis in this case. So this is classical. What's interesting is that if you suppose you have a non-conservative case like this, and you have no damping, which is the case we've just discussed, under some conditions you may find that equilibrium is stable, right? In this case, for example. If one adds damping to such a system, by example, one can show that you may actually destabilize the system. So the addition of damping to a non-conservative system may destabilize an otherwise stable problem. So it's a very curious kind of thing. And here's a published example in this journal here of that case. Okay. So I think I will stop it here. Next time I'll talk about continuous systems and see if we can generalize the energy theorems, Lyapunov and Chataev, to those cases. Okay? Thank you. Yeah. So you'll tell me how to do it, right? Okay. By email. Yeah. Okay.